Good morning or afternoon or evening, everyone. Thank you for joining us. My name is Yan, currently a visiting assistant professor of statistics and data science. I'm Muhammad bin Zayed University of Artificial Intelligence in Abu Dhabi. On behalf of the organizing team, I'm pleased to welcome you to the Spatial-Temporal Statistics and Data Science online seminar series. So our series brings together professors, researchers, practitioners, and students worldwide to explore Mises theory applications of space-time data. Our goal is to provide an avenue to share ideas and to spark conversations that push the field forward. We are grateful for the support of ASA section on Statistics and Environment, ENVR, the Royal Statistical Society's Environmental Statistics section, RSS-ESS, and International Environmetrics Society, TIES, whose communities help broaden the reach and impact of this series. Each seminar will run for 60 minutes, and the speaker will present for 45 minutes, and followed by 15 minutes for questions. Please feel free to type your questions into the chat at any time. We'll collect them and raise them after the presentation during the discussion period. And all the talks are recorded, and recordings along with the slides will be posted on our website. We typically host 1 or 2 seminars every month, and you are also very welcome to nominate future speakers. To stay updated on upcoming events, you can subscribe to our mailing list, and you will find more details as well as other resources at istsds.org. So with that, I'll turn it over to my fellow organizer, Jian, to introduce today's speaker.
Hi, I'm Jian. I'm from University of Houston and also co-organizer for the STSDS online seminar series. So it's my great pleasure to introduce today's speaker, Dr. Fabio Sigrist. And huge thanks to Dr. Sigrist for agreeing to present in this online seminar. So Dr. Sigrist is a senior scientist at the Seminar for Statistics at ETH Zurich, and he's also a professor of applied statistics and data science at Lucerne University of Applied Sciences and Arts. He obtained his PhD in stats from ETH Zurich in 2013, and his research interests include spatial-temporal statistics, mixed effects modeling, and Gaussian processes. And with that, I'm happy to turn it over to Fabio to begin his talk.
Thank you very much, Jan and Jan, for the introduction. Thank you, everybody, for being here and for giving me the opportunity to present some of our work. We are collecting questions. I've heard. For me, it's also completely fine if you ask me questions during the talk, in particular because it's an online seminar. And I think I might not need the full time of 45 minutes, given that I have only 16 slides. But yeah, we can also discuss questions, obviously, later on. So let me make this full screen. I hope you can see my screen. I'm not seeing the chat, so in case you have any questions, you need to unmute the microphone. Before I start, this is joint work with Tim Giger, a PhD student that will soon graduate in May, actually, and Reinhard for its methodology for Gaussian processes with a focus on spatial-temporal Gaussian processes applied to large-scale short-term weather prediction. So our motivating data set is the following one. We have daily maximum temperature and precipitation for 3,057 stations across the United States for slightly more than 1.5 years. So daily data. This gives roughly 1.7 million space-time observations. What you see here are three snapshots, four days, where we show spatial maps of maximum temperature, at 4 days across the conterminous United States. So I hope you can see my screen well and hear me well. Otherwise, please let me know by unmuting the microphone. I don't see the chat. I don't manage to see both of them somehow with the WebEx setting. Here's another figure to visualize the data. Here we have time series plots for 3 stations. Daily maximum temperature in Celsius. Apologies if you're more familiar with Fahrenheit. Daily maximum temperature and precipitation. We can see, and as you probably know, an additional challenge for modeling precipitation is that we have this mixed distribution. So we have days where there's no precipitation at all, which gives us a point mass at 0. And then conditional on that, we have positive rainfall amounts, which often are skewed. So we somehow have to deal with this. The models we're going to use are the following ones. Apologies. So we denote the response variable by y and predictive variables by x. More on the predictive variables later on. For temperature, we use a classical mixed effects models where we have a linear predictor and a Gaussian process denoted by B here that models structured variation in space some time that is not explained by the fixed effects linear predictor. The assumption of linearity can be easily relaxed. You could also use some machine learning models like neural networks or tree boosting. It's implemented in software already, but for the sake of simplicity, we're not doing it here. For the modeling rainfall precipitation, we have to somehow deal with this fact that we have this mixed distribution where we have point mass at 0, and then a positive continuous distribution. And the model we use is a transformed Tobit model. So we have the same Gaussian process as for a classical Gaussian likelihood, but then we apply censoring at 0, which gives us a point mass at 0. And then we have a transformation parameter that allows for skewness that is going to be estimated from data. This is a parsimonious model that has worked well in past works. The intuition is that this expression here, the Gaussian process plus the fixed effects term, can be interpreted as a precipitation potential, things such as a absolute and relative humidity and maybe other factors. If this potential is very small, there is a very low probability of rainfall, and if it rains, there will be little rain. If there's lots of humidity, absolute and relative one, there is a high chance of precipitation, and given that it rains, there's going to be lots of rainfall. So we have run process that governs both the precipitation occurrence and the precipitation amount conditional on occurrence. And we're not claiming universality of these models now. Obviously, there's other likelihoods that we could also apply, but we restrict ourselves to this type of model. For the Gaussian process, we use the whole methodology that we can present is very general. So we could use any space-time covariance function. It could also be non-stationary. We briefly analyze non-stationary, and we don't find a lot of, in our paper, and we don't find a lot of evidence for like this type of residual process that we have here. The model we're going to use is this non-separable space-time covariance function due to igniting. It's quite flexible with different smoothness parameters for space and time and interactions between space and time. Our framework is an empirical based approach. So we use empirical base for estimating hyperparameters. So we're being Bayesian where we need to be, which is the Gaussian process part, where we have essentially one sample per parameter. And we're being frequentist where we have repeated samples, so for the hyperparameters. Now we could longly discuss advantages and disadvantages of this method, such as maybe like ignoring type of the uncertainty, but also avoiding the need for any subjective priors for the hyperparameters. But that's the approach we use. And to deal with non-Gaussian likelihoods for which posterior distributions and marginal likelihoods are not available in closed form, we use a Laplace approximation. Well, I guess all of you know that GPs, Gaussian processes, don't scale well without any approximation for large data sets. And I guess I don't have to recall the cubic and quadratic time and memory complexity in the sample size for Gaussian process. So we need some approximations. Sorry. And we're going to use a vector approximation, inducing points, also called predictive process approximation statistics, and a approximation that we propose, a combined vector inducing points full-scale approximation. More on this later on. So the contributions that we present in this talk are this width approximation, this combined vector inducing points full-scale approximation. Then for non-Gaussian likelihoods with a Laplace approximation, but to my understanding also with other approximations such as variational Bayesian ones, we run into additional challenges as we will see later on. So for this computational challenges, for this we introduce iterative or Krylov subspace based methods and stochastic methods for width approximations. Now an important issue when you apply a vector approximation is how do you select the conditioning sets or neighbors. And we propose a scalable correlation-based distance neighbor search approach. We also implement GPU acceleration, and then we apply this to the large-scale short-term weather prediction task that I've mentioned in the introduction already. So some words on vector approximations. I'm not sure how familiar you are with these. At least I know from the people someone in the audience are very familiar with it. In brief, vector approximations work as follows. We have a joint distribution, a joint density here for our Gaussian process. This can be written as a product of conditional densities. No approximation so far. And then instead of conditioning on all sets of according to ordering that you have to choose, instead of conditioning all of them, we only condition on a subset of maximally a size MV, which is typically 20 or 30. We use 30 in the following. Yes, now these conditioning points are denoted as neighbors, vector neighbors, typically, and we also call them like this. Usually they are chosen as the, let's say 20 or 30 nearest neighbors according to some distance, usually Euclidean distance. Now, conditional independence implies, as you might know, sparse Koleski factors of precision matrices. So this is equivalent, this approximation, to the precision matrix being approximated by this sparse matrix here. In particular, we have a Koleski factors B here, or transpose one, that is sparse. This also gives a sparse precision matrix. Why does this work well? Well, intuitively, think of an AR1 process. An AR1 process is a Gaussian process with an exponential covariance function on the real line. Sorry, an AR1 process on the real line, I want to say. How does the precision matrix look like for an AR1 process? It has a non-zero diagonal, obviously, and it has only one two non-zero off diagonals. So conditional for a data point I, conditional on these two nearest neighbors on both sides, to the left and to the right. All the other points are conditionally independent. And the similar logic also applies for higher dimensions. This can be modeled theoretically also by the screening effect. And this is intuitively why vector approximations work quite well. In particular, experimental empirical research has found that in spatial applications, they often lead state-of-the-art accuracy. And if I may do some marketing or publicity for a recent paper that is going to be published in the Journal of Agricultural, Biological, and Environmental Statistics soon, we have done a runtime accuracy comparison of different GP approximations. Now, every GP approximation will at some point be very exact if you have enough computational budget, if you choose some tuning parameter to be very high. And now the crucial thing is for a given runtime, how accurate are you? And we found a very clear winner, which was the Vecchia approximation that for a given computational budget outperformed in almost all settings considered in this article, all the other approximations that we considered. Now, one challenge that we're going to discuss is choosing these conditioning sets, the neighbor sets. Kang and Katzfuss has nicely shown that for non-isotropic covariance functions, correlation-based neighbor selection, so using a correlation distance for choosing neighbors, works well and improves the accuracy. And that's actually what we're going to see also today. I was actually surprised when I saw those results, how big the differences are for our data set. The problem is this scales badly with the sample size. For some models where you can transform to an isotropic Gaussian process, Kang and Katzfuss call these Q-irreducible processes. You can still run your traditional machinery, for instance, using this algorithm by Ra and Kim, based on the Euclidean distance after transformation. But for many covariances, this is not possible. So for instance, for the space-time Gneitting covariance function, this is not possible. Also for the width approximation, we have this residual covariance that we were going to introduce soon, and where this is also not possible. Now, in a nice article, Abidata and co-authors presented the solution for exactly the covariance that we are going to use today, the space-time covariance. For doing this efficiently, correlation-based search, when you have data on a grid, on a regular space-time grid, then you can use some inequalities to do the search efficiently. This is not the case for our data. We don't have a regular grid, so we cannot apply this approach. So a few words on the width approximation that we propose. So Vecchia approximations excel in settings with low dimensional inputs, 2, 3, spatial and temporal, maybe spatial temporal data, and moderately smooth covariance functions according to the screening effect. While inducing point methods are better suited to higher dimensional inputs and smoother covariance functions. It's no coincidence that in machine learning, a lot of state-of-the-art Gaussian process approximations are inducing point-based ones. Because in machine learning, people often have higher dimensional input features. So width approximations combine the strengths of local Vecchia and global inducing point methods. And the basic idea goes back to what is called a full-scale approximation, introduced by Zhang and co-authors in 2011. It's a very neat idea in my opinion. So what you do is you decompose your process, your Gaussian process, into two parts. A low-rank predictive process part, BL, which has this covariance here. So you need to select a set of inducing points, which is usually relatively small, so that you can run calculations fast for this. So say 500 or 1,000 inducing points. In our paper, we also propose a novel approach for choosing these efficiently for spatial temporal data, but I'm not going to discuss it in today's talk. But once we have this, we get this covariance of the predictive process part. And then we have a residual process. The residual process has this covariance given here. And if you now just use the diagonal of this, you're getting a modified predictive process approximation, also called FITC in machine learning approximation. Now what we do is we apply a Vecchia approximation to this residual covariance. So the residual process gets a vacuum approximation. So this is clearly a covariance that is not isotropic. It's also not stationary, and we cannot just transform it to an isotropic one. So the question is, how do we choose neighbors for this? Before discussing this neighbor search, I want to briefly mention the following computational bottlenecks. So for non-Gaussian likelihoods with a Laplace approximation, you need to do linear solves and calculate log determinants of this matrix here. W is diagonal. It actually is the negative second derivatives of your log likelihood, but it doesn't matter. For the methods here, it's diagonal, and this is the Vecchia approximated precision matrix. So this is sparse, and even though we just add a diagonal to it, calculating a Cholesky factorization, which is the go-to method for like doing linear solves and log determinants, this has very poor computational complexity, which is also reflected in practice. So for spatial data 2 dimensions, this is approximately has n to the power 1/2 of complexity, and it's for high dimensions, it's at least quadratic complexity, which yeah, it scales very poorly. Let's say if you want to do 1 million data points. So we develop and use iterative and stochastic methods. In particular, for linear solves, we use the conjugate gradient algorithm. For log determinants, we use stochastic Lanczos quadrature, which is an established technique for calculating log determinants. This gives a stochastic estimator. Very briefly, how this works is that the log determinant is written as trace of the logarithm. Then this matrix here, our target matrix, for which we want to calculate the log determinant, this is approximated using a partial Lanczos tree diagonalization. Think of as an eigendecomposition, almost an eigendecomposition. This is diagonal instead of diagonal, but it's like an eigendecomposition if you're not familiar with tree diagonalization. Once we have an eigendecomposition or a Lanczos tree diagonalization, we can calculate the logarithm function of a matrix easily. We could just pull out the Q's, the orthonormal matrix Q, and we only need to calculate the logarithm of the inner tree diagonal matrix, which can be done very efficiently. And then the last step is to calculate the trace using stochastic trace estimation. If you put this all together, you end up with this, what is called stochastic Lanczos quadrature approximation. For gradient-based optimization, we want to calculate gradients of this log determinant. We also use stochastic trace estimation for doing this. And the nice thing of this approach is that once you have calculated a log determinant, so evaluated your likelihood or marginal likelihood, we're getting gradients essentially for free without any computational overhead. Another thing that we need to tackle is predictive distribution. We want to do probabilistic prediction, so we need predictive variances. And even though you can do solves efficiently once or maybe twice or maybe 100 or 1,000 times, if you do predictions for many points, let's say 100,000 times, running conjugate gradient 100,000 times is going to be slow. This is the same for the Cholesky decomposition. If you have a Cholesky factor given, even if it's given already calculated, running these solves, these triangular solves, sparse triangular solves 100,000 times will be too slow. So the way we circumvent this problem is we simulate from this posterior and then calculate sample variances. So then we need to calculate, run the conjugate gradient algorithm as many times as we have sample vectors, like say 1,000 times instead of 100,000 times or 1,000,000 times. Yeah, this was very brief, more details in the paper, but that's the machinery that we need to use. The devil is in the detail for these methods. In particular, preconditioning is very important. So it increases the conversion speed and reduces the variance in stochastic estimates. Preconditioning briefly means that the preconditions should do the heavy lifting, sort of, and the iterative methods then do the final polishing. So it's a method that kind of pre-solves the equation system. Then the preconditioned equation system can be efficiently solved with a conjugate gradient, or the preconditioned matrix for the log determinant can be calculated with small variance with stochastic Lanczos quadrature. In our paper, we analyze two preconditions, an existing one. We also propose a novel one for these width approximations. We analyze them theoretically and empirically. We obtain an approximate 1,000-fold speed up, so 3 orders of magnitude in simulated experiments compared to a Koleski factorization. So a substantial speed up. This allows for applying such width approximations for large-scale data sets up to millions of data points. Now this is another topic, but I've mentioned it before. How do we choose the conditioning set in Vecchia approximation? Be it standalone Vecchia approximation or Vecchia approximations in width approximation, where we have the Vecchia approximation for this residual process. Kang and Katzfuss nicely show that correlation-based selection of neighbors improves accuracy of Vecchia approximations. And this is based on this correlation distance. So we calculate the correlation between 2 points, either for the residual covariance in width approximations or for the covariance itself for standalone Vecchia approximations, and we convert this into a distance. And now we're choosing as nearest neighbors the ones for every data point that in the previous in our ordering previous data points with the lowest distance to a data point I, according to this distance. Now, how do you do this computationally efficient for large data sets? And it turns out that standard neighbor search methods don't work well for this correlation distance. So KD trees are tailored to Euclidean or Minkowski geometry. Ball trees, for ball trees, pruning is less effective. So we had to search for something else, and the cover tree algorithm is an algorithm that is specifically designed for general metrics. And we modify and extend the cover tree algorithm in 2 ways to tailor it to Vecchia approximations. And the crucial difference compared to general applications of the cover tree algorithm is that we search only the nearest neighbors among a subset. So those points that are previously in the ordering that we use. This means when we construct a cover tree, we insert as a next child always the point that has the smallest index. So we cover tree partitions the data iteratively in smaller subsets, and for every such potential set we always choose the smallest index. This has the advantage that when we do the search for a point, let's say data point within index number 6 here in the figure, we go down the tree. Once we reach a point with a higher index, we know that all other points in this potential set here, and in particular also for lower levels for this child 8 here, for this node 8, we'll have a higher index, so we can stop the search here. It doesn't look like a big thing for this small data sets, but for large data sets, this results in a big speed up. And another thing we do is we partition the data into equally sized sequentially ordered subsets, and this allows us to apply the cover tree in parallel. The full data before applying the cover tree is partitioned into different subsets, sequentially ordered subsets, and then we can trivially parallelize the cover tree. So this makes the cover tree, this variant, feasible for large data sets, even on a CPU without GPU acceleration. Sorry, I wanted to briefly check whether the connection is still there. Here we are. So I'm briefly presenting some comparison of this newly proposed width approximation with Vecchia approximations and modified predictive process, or FITC approximations. So what we see here is prediction accuracy. We sample 10,000 train and test data sets. And we show here prediction accuracy versus dimension. So we have 2-dimensional data, 5, 10 dimensions, 20, 50, and 100 dimensions. Root mean square, log score, and CRPS, but no matter which metric we use here or which measure we use, it's always the same story. The blue line is a Vecchia approximation. Green line is a low rank modified predictive process, or FITC approximation. The red line is a WIF approximation. So for low-dimensional input spatial data, vector approximations are very, very accurate. In other experiments that we have done, we often find the vector approximations are essentially equivalent to exact calculations for money covariance functions and data sets. Now, low rank approximations are considerably less accurate. As the dimension increases, vector approximations become less accurate. At some dimension, inducing point approximations are more accurate, actually. And intuitively, this is due to some form of cursive dimensionality. It's just harder in higher dimensions that, say, 30 or whatever, 50 or 60 nearest neighbors contain all information such that conditioning this, there is no residual correlation. And the WIF approximation is most robust here as the dimension grows, has the highest accuracy, whereas vector approximations deteriorate. Now, to be honest, yeah, in spatial and spatial-temporal statistics, we're somewhere here. And we're going to see whether we see a difference. As a spoiler, I can already mention now that for spatial-temporal data, we don't see a big difference also in our application. But for high-dimensional inputs, as it's often used in machine learning, that there is a considerable difference. This is not a rigorous runtime accuracy comparison. Vector slightly faster, but even if we increase the number of neighbors such that we have equal runtimes, the results look relatively very similar. Also, when using other hyperparameters, we find similar results, and when rigorously measuring the accuracy runtime trade-off in other manners, we get qualitatively very similar results. Yeah, so much for the WIF approximation. And the last thing I want to mention before going to the application is GPU acceleration. We implement GPU acceleration by offloading several operations to a GPU. In particular, dense linear algebra operations, mostly with cross-covariance matrices, so products and solves, sparse matrix multiplications with the vector matrices, and also vector neighbor searches. We implement them using NVIDIA CUDA routines. We've also tried implementing, or we have actually implemented also the construction of the vector factors on a GPU, and we did not get speed up there for potentially for various reasons. The CPU implementation is already quite optimized, and there might be overhead due to the way our code is structured. So our code is quite flexible in terms of covariance functions, our code base that we can use. So we would have to do a lot of rework and parallel code implementation in CUDA to maybe see a speed up also in terms of vector construction. So these are some experimental results. Maybe if we focus on the right-hand side plot here, this one, we see a speed up comparison, GPU versus CPU. The CPU that we use is I don't have the exact result here in the slides, it's in the paper, but it's quite a competitive CPU with quite a few cores, if I remember it correctly, 48 CPU cores. For WIF approximations, the purple line, and vector with a correlation-based neighbor search, the pink line, we're getting in a speed up of 1 order of magnitude. So substantial additional speed up with GPU acceleration. Less speed up than when going from Koleski to iterative methods for non-Gaussian likelihoods. But these experiments are for Gaussian likelihoods, by the way. But for non-Gaussian likelihoods, we see very similar results. Yes, and for the remainder of the talk, I'm going to present the results for applying this to a short-term weather prediction. We're applying this methodology that I've presented in the previous slides, including all the scalable methods, to modeling daily temperature, maximum temperature, and precipitation. We include a large set of predictor variables, coordinates, climatographic variables, physiographic variables, nonlinear transformations, interactions between them. I have a slide in the appendix if you're interested in it. And the Gaussian process uses this space-time, non-separable space-time Gniting covariance function that I've had on the slides, some slides before. We produce forecasts for multiple days ahead, so from 1, 2, 3, 4, and 5 days maximally for precipitation. Sorry, for temperature, and we do this daily. So using an expanding window training data set with the year 2024 serving as initial training data set. So starting on December 31 in 2024, we produce forecasts for the next 5 days, and then we shift the window by 1 day. Do forecasts again on January 1st of 2025 for the consecutive 5 days, and so forth. Covariance parameters are re-estimated at the end of each month. This depends on the approximation that we use. Approximately for the more computationally heavy approximations, 1 hour, maybe for the slowest one, 2 hours. So it technically would be operationally feasible to run this daily, but we do it at the end of each month. Prediction is very fast. It's almost instantaneously, a few seconds. Yes. To evaluate prediction accuracy, we additionally randomly select 25% of the stations that we leave out for training. So we're doing predictions for holdout set that is both spatially and temporally out of sample. These are the results for modeling temperature. We fixed the matter smoothness to 1.5. It's unfortunately currently not yet implemented on a GPU because of this Bessel function. When estimating it on a subset of the data using a CPU, we obtain something that's very close to 1.5. Now, what do we see here? We have the root mean square and the CRPS. This, what's the name of this color? Green, turquoise, or dark green color here is a persistence forecast. The almost flat or horizontal light green line is a fixed effects only forecast. So we're using the same predictor variables, but don't include a Gaussian process. So this allows us to analyze what is the advantage of or the added value of a Gaussian process. The red and the orange lines are low rank inducing point approximations. They perform very badly here. Also with our novel space-time selection of inducing points, so I'm not going to discuss them. The more interesting parts are these 3 remaining methods. So the blue line, light blue line, is a vector approximation where we select neighbors using the Euclidean distance. The pink line is a vector approximation where we select neighbors using the correlation-based distance. And you see there's a substantial difference for lead times where a Gaussian process matters. So for 1, 2, and up to 3 days ahead. Afterwards, we have the same accuracy as just a fixed effects baseline. There is a substantial difference. What is it? Approximately 10%. A width approximation gives essentially equal prediction accuracy. And the same story also for the CRPS. Correlation-based neighbor search clearly improves upon Euclidean-based neighbor search. With approximations, these combined vector and inducing points full-scale approximation gives similar results, which is in line with the results we had before, where we only start to see differences in higher dimensions. For precipitation, we have the following results. We use a shorter prediction horizon. We only go 3 days ahead because it's just harder to predict precipitation. That there is it's more difficult. So we click the predictability, but the statistical predictability is quickly saturated, so to speak. We use 0.5, so as smoothness parameter, an exponential covariance. No, it's not an exponential. Yeah. It's this space-time covariance function of knighting, but if it were purely spatial, it would be an exponential. But we use 0.5 as smoothness parameter. Estimating this on a subset of the data gives something, using a CPU gives something very close to 0.5. For both Vecchia approximations and WIF approximations, due to the non-Gaussian likelihood, we use iterative methods. We distinguish between precipitation amounts, which we evaluate using the mean absolute error and the CRPS here on the left-hand side, and precipitation occurrence, binary precipitation occurrence using the Brier score and the log score. But the results are qualitatively very similar for both of them. A persistence forecast, sorry, the dark green or turquoise line is very bad. A fixed effects only forecast where we have no Gaussian process is the green horizontal line. Vecchia approximation improves upon this, and we again see a difference between correlation-based selection of neighbors and Euclidean ones. So the blue line here, the Euclidean, the pink line, correlation-based difference. So the scale here is quite large because some methods are very bad, but it's quite a substantial difference. No big difference between WIF and correlation-based Vecchia for point predictions. For the CRPS, we see some improvements of the WIF approximation compared to a Vecchia approximation, also correlation-based. The situation is slightly reversed for the binary precipitation occurrence, where correlation-based Vecchia is marginally better than the WIF approximation. Overall, WIF and correlation-based Vecchia perform best at short lead times, very similar as for the the temperature data. And yes, that's it almost. So to wrap up, we demonstrate that non-separable spatio-temporal Gaussian processes can be scaled to very large weather data sets with the approximations that we use, Vecchia and full-scale Vecchia approximations. Iterative methods and GPU computations are important, in particular for non-Gaussian likelihoods. WIF and correlation-based Vecchia approximations give the overall best accuracy, with a correlation-based Vecchia approximation given the clearly best speed accuracy balance. In our application, we see that GP-based methods improve short-term weather prediction for both temperature and precipitation with respect to several baselines. Unfortunately, we do not have NWP forecasts. It would be very interesting to compare this to these. This is a future work that we could consider if we have access to this. Other future work would also include considering other likelihoods for precipitation, for instance, or extending these to multivariate models. There's many different directions for interesting future work. I just want to briefly mention that all the methods that we have presented today and in our papers are implemented in a C++ library called GPBoost with high-level Python and R packages. If you want to know more about this, have a look at this GitHub page. Here are some references, in particular also these two papers here by Giger, Reinhard Fuhrer, and myself, where we present most of the methodology, or actually all the methodology and application that I've presented today. Yes, that's it all from my side. Thank you very much for your attention, and I'm more than happy to answer any questions.
Yes, thank you for sorry. Thank you for your talk, and yeah, I do have a few questions. I hope that won't take all the time. First question is, you mentioned that when in your mixed effect model, there are some works that use a neural network or another model for the mean structure. I wonder if it is a kind of established method in the literature, or it's a...
Yeah, it's a good question. I mean, obviously, neural networks are highly popular nowadays, right? For tabular data, tree-based methods are also very accurate. So I would say the go-to methods are neural networks, tree boosting, and random forest. I think all of them are established. The GPBoost library that I mentioned implements tree boosting actually also. So all this methodology combines very nicely with tree boosting. If you want to extend this to using tree boosting, you can directly run this out of the box. So replace the linear part with a nonlinear model jointly, and that's interesting, jointly estimating hyperparameters and the nonlinear function. So not a stepwise approach that is often suboptimal, but jointly estimating this with G-boosting, so that's possible, yes.
Yeah, I see. Thanks. And a second question is in the estimation of the likelihood, maybe also for the prediction, you mentioned for one component you use the conjugate gradient. And for the other component, there is a stochastic approximator. I wonder, so for the conjugate gradient should be a iterative method. I wonder if the number of iterations and how its impact on the gradient computation. Well, I mostly use the auto-diff functionality. I wonder if it have some
I
impact
see.
on that.
Yeah, good question. The number, if you have a good preconditioner, the number of conjugate gradient iterations is usually moderately low. So it needs to be low in order to be efficient, computationally efficient. I don't have exact numbers here, but it's usually quite low. I'm not even sure if we analyzed this in this paper. In other papers, we've analyzed it. I have a little bit of criminal record on this topic, so this is not the first paper where I've done something like this. Automatic differentiation is a very good point. I'm not sure how this combines. I guess it's a little bit that's going to be tricky with automatic differentiation. I mean, in our software, we don't do automatic differentiation. We have all gradients calculated analytically, which is possible, which even for the vector approximation, for instance, gives us some simplification. So I wouldn't run automatic differentiation when you have something like a vector approximation blindly. I guess you can get big speedups if you do this smartly, at least partially analytically. To my understanding, in machine learning, there's this GPyTorch library, and if I'm not mistaken, they do use automatic differentiation, but I would have to think about carefully whether I see the potential issue, but I cannot give you a straight answer right away how this works. Yeah.
Okay, thanks. And if time allows, a quick question is, you show the results for the FITC and the results for Vikia and the VIF method, and somehow the VIF isn't really a average between FITC and Vikia. So in the precipitation example, or even in the temperature example, the FICC actually underperforms a fixed effect model, and the VIF didn't underperform Vikia. Is there some interpretation or understanding for that?
Yes, a good question. Thank you. So I mean, I'm not sure if you see my slide still. I mean, it's not an average. It's a very, this full scale approximation, which goes back to Sang et co-authors, is a very smart approximation, if I might call it like this. So you really first have your your predictive process approximation, and then on the residual part, you apply the Vecchia approximation. So in that sense, it's almost like guaranteed to improve both Vecchia and FITC approximation. If the FITC approximation doesn't model your signal well, then the Vecchia approximation can take over. Now, obviously, if the Vecchia approximation is also not able to do the job, then it will not run. But if the Vecchia approximation is accurate, then this residual approximation in the VIF approximation will also be accurate. That's not a theorem, but that's my intuitive understanding, and that's what we see in all experiments that we have done. Yeah.
Because I think the fixed effect model is a special case of the FITC. So FITC underperform fixed effect because of a sort of overfitting. And
yeah, I guess so. I guess so. It's a good question. Why does the FITC? I mean, there's some form of extrapolation that we do, right? Temporal extrapolation. And yeah, maybe due to overfitting or over smoothing, it performs very badly, worse than without the GP. So yes.
Yeah, so the question is the overfitting of FITC somehow is curbed by the VIF method when it's combined with the Vikia.
Yes, and just, I mean, intuitively, we're not doing first a VIF and then having our Gaussian process prediction, and then on the residual, like in a two-step approach, then correct this with Vecchia. It's all done jointly. It's really one joint. If you like, you can also see this VIF approximation as a general form of a Vecchia approximation. In this general framework of Vecchia approximations by having additional conditioning sets, which are these inducing points. So in that sense, it's not like applying first an FITC and then doing a two-step approach. It's really a combined approximation that kind of directly corrects for everything that the FITC could potentially do wrong. That's my interpretation, yes.
Okay, thank you. That's all my questions.
Can I ask some question? So thank you for the talk, very nice and clear. So maybe following up on Jian's question for the residual approximation, maybe slide 7, when you are showing this decomposition, I'm wondering if this different part of process has actually different sparsity covariance matrix.
Yes, thank you for the question. So, I mean, we have this is the residual covariance matrix. And then we apply a Vecchia approximation. So is the sparsity, so if I understand your question correctly, is the sparsity different to directly applying a Vecchia approximation, a standalone Vecchia approximation? Is that the question? I don't think so. Yeah, no, maybe it is actually. I mean, even if we use the same ordering, and we're using a random ordering here for this very large data set, then different neighbors are selected. So the sparsity factor, the sparsity of the Koleski factor is the same, right? It's always per row. It's 30 number of Vecchia neighbors, but the precision matrix might have a different sparsity structure. Yes. But if you apply iterative methods, it doesn't matter what is the sparsity pattern. This matters for Koleski decomposition, but not for iterative methods, because you multiply with this B or do triangular solve with B, the Koleski factor, the sparse one, and not the joint precision matrix.
Yeah, that's interesting method. And another question is on the GPU computation. They are showing very nice speed up. So I'm wondering, what are your experience with the like the improvement? Are they like doing this parallel very well, or like the architecture is helping a lot, or what would be the reason that the speed up?
Yeah, it's mostly, I mean, the two main reasons is these for the FITC and VIF. So everything that has a low rank part, a inducing point or predictive process part, is all the matrix vector and matrix multiplications with these cross covariance matrices, which is just very trivially parallelizable on a GPU. So this is one part, and then the Vecchia neighbor search can also be done very efficiently on a GPU. I mean, there is some speed up, but it's actually, I mean, to be honest, it's lower than I initially thought. I mean, given that, for instance, if you have a Koleski decomposition and you go to iterative methods, you have a 1,000-fold speed up, and here you get an additional, depending on the type of approximation you use, additional 10 times speed up. So it's there, but it's slightly lower than I expected, but it's actually also in line with what other people report. If you look in the machine learning literature, or people have done this also for vector approximation in the statistics literature. So it's there. I often try to design methods that also run on the standard laptop, so with a CPU, but obviously it's nice if you have additional speed up with a GPU. Yes.
Yeah, thank you.
Thank you for the question.
Thank you for this interesting talk. I also have a question. So it's about the correlated based vector. So when we choose using this correlation, so can we have you ever kind of visualize the neighbors based on the correlation and compare it with the original vector?
No, I have not, but it would be, I guess. I mean, it depends on you. You mean the standalone vector approximation for this space-time covariance? I guess it depends also a lot on the hyperparameters that we have, like these different range parameters and smoothness parameters. It's even more challenging for this residual process in the width approximation, which is non-stationary. I have not, but I guess it would be quite interesting and give interesting insights. So it's a good idea, but I've not done it. Yes.
Yeah, because it has an improvement on the performance. So I was wondering.
Yes.
Yeah.
Yes.
Okay. Thank you.
Thank you.
Is there any other question?
Yeah, so if there's no more question, yeah, let's conclude the online seminar today. And thank you very much, Fabio, for the excellent talk. And yeah, have a nice weekend.
Thank you very much. Goodbye to everybody.
Okay. Thank you. Bye-bye.
Goodbye.
Thank you.